Algebra 2, Section 2.7, Parent Functions and Transformations. Objectives. Identify and use parent functions. Describe transformations of functions. Vocabulary. Family of graphs. Parent graphs. Parent function. Constant function. Identity function. Quadratic function. Translation, reflection, line of reflection, and dilation. The parent graph is the simplest form of a graph of a particular family of graphs. The different family of graphs that you will see in this section are the constant function, the identity function, the absolute value function, and the quadratic function. The constant function is just a horizontal line. So here we have just a horizontal line. This could be something along the lines of maybe y is equal to 4. So we just get y is equal to a number, and that gives us our constant function. In this case, it's actually y is equal to 1. The identity function is just the equation y is equal to x. Everything that y is, x also is. So say like in this point right here, we have x is 2, y is 2. At this point down here, we have x is negative 4, y is negative 4. So it's the identity function. We have the absolute value function, where this one, as we learned earlier, has the equation of y is equal to negative x on the left side and y is equal to positive x on the right side. And then the last one we have is the quadratic function, which is y is equal to x squared. Identify the type of function represented by each graph. Well, this first one right here comes from the quadratic family. And the second one looks like it's going to be coming from the identity family because it's just a line. And if we go back, we should see that those are the cases. So the quadratic function, or the quadratic family, gives us that parabola. And then the only other one which has a line, well, there's two. There's the constant, but that's a horizontal line. And then there's the identity function, which is a slanted line. And in this case, we do have a slanted line, so that would be from the identity family. All right, so now we're going to have different types of transformations. So first we're going to start off with vertical shift, and I'm going to use an example here of the quadratic family. So we have our y is equal to x squared. And if we have a translation upwards, then we could get something along the lines of y is equal to x squared plus 1. So what it says here is that for translation k units upwards, where k is greater than 0, meaning it's positive, we have y is equal to f of x plus k. So in this case, our f of x is the x squared, And here we're just adding to it plus 1. And then for k units downwards, it would just be y is equal to x squared minus 3. In this case, our k is equal to 3, and the minus is just saying that we're moving downwards. For this one, our k was equal to 1. And the plus or minus sign is just the translation up or down. Next one we have here is the translation h units to the right. So here is a little bit different. So what I'm going to do is something on the side. I'm going to say I'm going to take this one right here. And I'm going to say x minus h. I thought I fixed it. We're going to get x minus h. I can write. Equals 0. And I'm going to go ahead and I'm going to add h to both sides of the equation and get x is equal to h. Since x is equal to h and it's a positive h, we're going to be moving in the positive x direction, which is the right direction. If we do the same work for this one will just simplify to x is equal to negative h, which is then a translation in the negative x direction, or to the left. All right, so what does this look like? Well, for h units to the right, what we're going to do is we're going to have y is equal to x minus, and let's use the same number of 1 this time, squared. So what's happening here is we're plugging it into the squared business. Our h is the thing inside of the squared, or inside of the absolute value, or if we ever got there, inside of the square roots. The horizontal translation is there's always something happening to it besides just plus or minus. Whereas the vertical translations, the vertical shifts, those are just a plus or a minus. Okay, for the right, or for the left, this would just be a y is equal to x plus 3 squared. And once again, if you set what's inside of the parentheses equal to 0, you'll get that your x is equal to negative 3 for the left, and x is equal to positive 1 for the right, and hopefully that'll help you realize why you're moving to the left or to the right. And there's more translations, more transformations. So we also have vertical stretches, vertical compressions, horizontal compressions, and horizontal, well, I just wrote that twice, okay. One should say stretches. Let's see, which one is it? This bottom one should say stretch. Okay. So I'm going to just go over the vertical ones. So just using our y is equal to x squared. What would this look like? Well, this would look like something, if we're getting a compression, like a y is equal to like 0.225. When I put the iPad down, I get all those weird issues. 25x squared. And then for the stretch, we would get something like y is equal to 4x squared. So for the compression, which we did here, the number we're multiplying our f of x by from the parent function is less than 1 but greater than 0. It's a decimal number, which is less than 1. Our stretch, on the other hand, is a number greater than 1. So 4 is greater than 1. It's not much, but it is. So what we're doing is, for the first one, is whatever we get for our x, we need to square it, which makes it larger. Then we multiply by 0.25, which makes it smaller again. So that's why it's a compression. For the stretch, we're going to square some sort of number, and then multiply it by 4, which is a larger number, which will just make it larger all in all. All right, I'm going to skip the horizontal compressions and stretches because they're basically just the same thing as our vertical stretch and vertical compression, except they're flipped around. A horizontal compression is the same thing as a vertical stretch. Math is slightly different. I'm just going to go over the vertical stretches or compressions. A horizontal stretch is the same thing as a vertical compression. So if we have a vertical stretch, let's just say we had a graph which originally was this. When it gets stretched, it gets taller. And those should be touching each other, but they're not. So that one gets taller faster. Well, that's the same thing as a horizontal compression, because it's going up faster, which means that it's not quite going out as fast either. It gets compressed, squished. Okay. And then the last one is reflections in the x and y axes. So in this case, this would be something along the lines of y is equal to negative x squared, keeping in mind the squared doesn't get rid of the negative. And it doesn't really help with this example with my x squareds. It doesn't really help with a lot of the things we're graphing today, but this one could also be seen as y is equal to a negative x squared. In this case, it does actually destroy the negative, and you don't really see this reflection because parabolas are symmetric, so when they switch, you see the exact same thing. So not the best of example for that one, but let's just go ahead and move on. All right, so we're going to describe the translation in y is equal to x plus 2. Then we're going to graph the function. All right, well, this right here, if you recall, that was just a vertical shift. There's my abbreviation of up by 2. Since it's plus, we go up. So let's go ahead and give this a quick graph. So we have our x-axes, we have our y-axes, and as I was saying before, we're going to get slopes of y is equal to x. That means we hit every single corner, and then y is equal to negative x. There we go. And since we're doing a vertical shift of 2, I'm going to go ahead and I'm just copy this. I know you have to use paper. You know, before I copy it, I should finish it and put arrows on there. Now I'm going to copy it. And I'm just going to move this upwards and change the color. So we said up by 2, so that's that. And I'm going to change the color to pink, and there you go. It's the exact same graph, just moved up 2 units. All right, so describe the reflection, then graph. So I'm going to go ahead and get my graph started. So this one is a parabola. We can scroll back. For you, you have to scrub backwards because you're watching this online. But I could scroll back and I could look at these different graphs that we have here. And we see that we have a parabola, which I'm going to go ahead and graph right now. And our parabola, in this case, has key points of 0, 0, 1, 1, and 2, 4. And as I was saying, it gets reflected. We get the exact same ones on the other side because it's symmetric. And we get something which looks vaguely like this. It should have a curvy bottom, but I'm not the best at doing that. All right. And as I was saying, this is a reflection, and it is a x-axis reflection. So that means I'm going to get all those same points, except I'm going to reflect them about the x-axis. So we had 0, 0. That one doesn't reflect much. We're going to get our 1, 1, and then we're going to get our 2, 4. And then we'll get the same ones on the opposite side, and we get a parabola, which if I was good at drawing would look exactly the same, but it's not. It's pointing downwards. kind of looks a little bit like DNA, except sideways. Okay. Describe the dilation, then graph. So here we have y equals 4x. So this is a vertical stretch by a factor just means multiple, by a factor of 4. Okay, so we should be comfortable with this graph. We've seen this graph. This was a lot of chapter 2. So if we had our original graph, we would have our identity graph with 0, 0, 1, 1, 2, 2, 3, 3, and so forth, and just continuing that on forever. Then it goes down the other way also. And what we're going to do here is we're going to stretch this by 4. So we're going to multiply each one of those y values by 4. So 0 times 4 is, okay, well that's still 0. 1 times 4 gives me 4. 2 times 4 gives me 8, but that already goes off my graph, so I'm going to go ahead and just kind of graph this how I have it. And then hopefully there we see that it got stretched upwards by 4. It's going higher, faster. Bigger, stronger, faster. How does the Captain Marvel thing go? Whatever. All right, last example. We got this. Ethan is going to add a brick walkway around the perimeter of his vegetable garden. The area of the walkway can be represented by the function f of x is equal to 4 times the quantity of x plus 2.5 squared minus 25. Describe the transformation in the function, then graph. Okay, so we got everything going on here. So first off, let's highlight. We have this x plus 2.5. That right there is a horizontal shift. HS is horizontal to the left by 2.5 units. We're going to have a vertical stretch. This one I'm actually going to write out. By 4. And then lastly, we're going to have, which I guess I'll do in yellow, this vertical shift down by 25. Okay. Well, I was just thinking, how am I going to graph this? And the answer is, I'm going to get creative with it. So that vertical shift downwards of 25, I'm not even going to write my x-axis. I'm just going to go ahead and say that this right here is negative 25. And then we'll just find out where everything else is from there. There we go. All right, well, that's negative 25. Our y-axis is at x is equal to 0. So we can move this to the left by 2.5. So that's going to be 1, 2.5 over. So there's our first point. And if we didn't have the vertical stretch, we would have a point right about here, about 1 up and 1 over. But we have the vertical stretch of 4, so we're not going 1 up and 1 over. We're actually going 4 up and 1 over. And I get another one over here, and I'm going to, okay, so what is that number? So it's a 25 minus 4. That number is a negative 21. This down here is a negative 2.5. Can we see that? We can. It's a little small, but we're good. And because this graph is stretched really high, I'm going to just go ahead and draw it. Keep in mind that this point is if there was no vertical stretch. But there is. So we just took that number, that up by 1, and multiplied 1 by 4, and it got a little bit higher. All right, folks, that's it. That's probably the longest one I've done so far for Algebra 2.